Thank you, House. Thank you so much for being here. We're super excited to hear what you've got to share.
Yeah, great. Yeah, I guess I will take over. Can everybody see my screen? Good.
Yes.
Okay. Yeah, I'll take that. Yes. Okay, cool. So today I will present this topic on what do humans care about agents. It's mainly be around my work called AutoLibra. This is a collaboration with a lot of amazing folks at the Stanford NLP and beyond. And there's my website, how.computer. You can check out that for more info about me. Uh, just to give you a little bit background of myself. So I'm currently postdoc at Stanford. My research is mainly on autonomous AI agent and how to bring this agent closer to humans. I think one of the uh, very underappreciated and missing piece in AI agents right now is the lack of the social intelligence. So social intelligence is the capability that actually bring humans together, allows us to understand each other's intent, belief, and coordinate, collaborate, communicate with each other. And my a large part of my research is to build social intelligence in autonomous agents, and using this way, we can study what are the new dynamics of a human-agent interaction. So this talk will be on this topic. I will be talking about a recent work about in this direction. So I know this is a redundant slide for a lot of folks. Like agents is a very popular topic here, but let me give a recap on what's the definition, what a typical agent is like. So agent is like in this loop, right? So agent have some input that will normally include like a task description. It could be from the user, could be from the developer. And the agent can receive like messages from users. It will also observe a lot of like observations from computer screens, from terminal messages, or from other tags or multimodality inputs. And based on these observations, the agent will produce actions, which are control signals to operating systems or internet or to callings and the messages to users, etc. So basically, agents are trying to output this action to influence the environment. As a result, the environment will change its own state and produce a new observation to agents as the next round of the agent's input. So agents are constantly in this interaction. So different from most from conventional machine learning models, it is not just input output. It also need to consider the actions, the future influence of the actions. It's not just to output the correct action at each step. So this actually makes the agent problems a lot harder and more interesting and closer to real world applications. So one thing that often bugs me about the agent is the agency evaluation. So I think agency evaluation is by and large lags behind the improvement of the applications. So ever since 2013, people have been fascinated about this like autonomous AI agents powered by deep neural network. One of the representative work at that time is Atari games from DeepMind. The evaluation of Atari games is very straightforward because Atari games were built for human players. So there are evaluation of the game success baked in these games. So you can just use a game scores with some normalization as the reward, as the evaluation for the AI agents. So similarly, after several years, people began to study embodied agents, simulated robots, or 3D games. This is one of the work from CMU on MineRL, and there are challenges after that. The evaluation is based on the progress. So the goal of the MineRL is to mine diamond, and everything that can contribute to mining diamond can be counted as progress. And the final evaluation is based on the accumulated reward of the items that the agent acquired in order to achieve the diamond. So this is for MonRL. And third work I put here, this is one of my own work collaborating with CMU folks in 2023. It's called Web Arena. So the tasks are more realistic than the previous ones because it's realistic website. We have a self-hosted or website that are very similar to their real-world counterpart. And we give them a lot of tasks that we normally do in our daily life. And the agent can use actions like the playwright actions, tool calling, or use a keyboard and mouse events to interact with the websites. And in the end, so the evaluation is based on the agent's final outcome. So agent needs to stop at the right place, the right page, and we will analyze the information on the page and the URL on the page to understand whether the agent has completed the task or not. So basically, you can see, although the evaluation are different, like the game scores, the progress, and the task, but for all of these cases, the agents are all evaluated based on like a verifiable and external reward that is pre-programmed by the developer. So there are some problem of this. I think this mainly lies in the mismatch between the assumption and the reality. So first, I think the first assumption is that the goal of the agent is known and encodes all of the requirements, which means that the developer already know what the agent is going to be used for. And the instruction and the task description often encodes all of the requirement. For example, if I say I want to buy a pair of socks, the evaluation is to just check whether I have a pair of socks in my shopping cart. But the real world tasks are often open-ended. Sometimes when I say I want to buy a pair of socks, I might have some, for example, preferences about socks, right? I don't want a pair of yellow socks. So even if the agent have buy a pair of yellow socks in my cart, I may not see that as a successful. And it can be even more open-ended. Maybe I just want to shop some clothes and I may not specify what kind of clothes I want to buy. So real-world tasks are often open-ended at the first. When the task is given to the agent, the goal may not be known and it may not encode all of the requirements. It's only when the agent has conducted the task, I know that the users will know that whether the agent have completed the task that is in their mind. And the second assumption is that only the end state matters. So in all of the cases I introduced before, we only evaluate the end state of the game or at the end state of the trajectory. Only the end state matters. But in reality, we may not just care about the end state. We also care about the manner that the agent used to complete this task, in which the agent completes this task. For example, let's say closing a door, closing a car door, right? So if we only evaluate the end state, we only need to check whether at the end of the trajectory, whether the agent has closed the door or not. But we might also care about how you close the door, whether you close it gently or slam it. It's a totally different thing for us as humans. But if we only evaluate the end state, then the manner is not controlled and evaluated. And lastly, I think even more important is that we know, the assumption is that we know what people care about agents. As a developer, as the agents, as the people who train the agents or build the agents, we already know what people care about the agent, and we evaluate on the things that we think what people care. And I think the reality is we don't. And I will show you the example later. great. So that's the reason why we built this work called AutoLibra. And the idea of AutoLibra is to investigate how to evaluate the agents based on the human feedback. I will also talk about how to improve agent in the second part of this talk. And this is what I want to emphasize, that the human feedback that we collected is open-ended. So we don't really want the human to give like a numerical Likert scale kind of feedback. We want the feedback to be as natural as possible, and it make this task even harder. So there's as a part of the apart from the goal-oriented evaluation I mentioned before, I do observe a rising trend of behavior evaluation of the agents. So for goal-oriented evaluation, most of the tasks are operating system kind of related tasks like computer use agent or like AI software engineer, SWE kind of task, and or the internet or the browser use kind of tasks like web navigation or deep research, etc. So there are several amazing work, amazing benchmark on this in this category. And behavior evaluation, on the other hand, are mostly applied to the tasks that are involving users and interaction between the agents. For example, the collaboration or like the agent that work as the assistant. And for the agents, we can there are also tasks like social interaction between the agents or multi-agent systems. So there are some relatively newer work like CoGym, Zootopia, multi-agent failure work that are falling into these category. So um, I have already talked about the problem of a goal-oriented evaluation. The benefits of it is that it's verifiable and it's often objective. It's often implemented as a pre-programmed task evaluation metric. And the problem is that it's end-to-end. You don't really evaluate the internal state of the trajectory. For example, WebArena check the result or the final page. So there are several ways that we evaluate the agent's task completion. And for behavior evaluation, we are evaluating more concrete behavior that the agent take. Just as I said, this can evaluate the manner of the agents, but it often requires manual expert design. For example, this is my work called Zootopia, where we simulated the social interaction between agents or between agent and humans. And then we are evaluating it based on 7 dimensions that are grounded in the literature that we designed beforehand. So I think for with a behavior evaluation, it can solve some part of the problem, some part of the assumption reality mismatch I mentioned before. So previously with a goal-oriented evaluation, only end state matters, but with a behavior evaluation, we also evaluate the manner of the goal of the agent's behavior.
Hey, Hao, could I just ask
So
a
yeah,
question about this?
yeah, yeah.
I uh, I see what you're saying, but I also am struggling to think about um, what kinds of consequences of behavior cannot be represented in the end state. So, like you mentioned, the idea of slamming the door hard. We might think that, okay, maybe we measure behavior, but we could also just measure the end state and also measure like was the door damaged or not, right? And so the consequences of that misalignment is actually represented in the end state, and then it becomes an end state evaluation. Like I kind of wonder how you think about the differences, if we're willing to accept like a broader definition of what end state is here.
Okay, I think there are 2 aspects. One is that like we cannot, not all of the behavior are encoded in the end state. Just as you said, if I slam it really, really hard, maybe the door is damaged, the window is broken, etc. In that case, for sure, we can evaluate the end state, but probably it only is a loud noise, right? That will, most likely if you evaluate at the end state, you cannot really observe any differences between different manners. Or sometimes it's so sneaky and the user may not really check the middle of the trajectory. For example, let's say you have an agent, you ask it to buy some stuff and you give it a credit card, right? The end state is that the agent is checking out the stuff that you want, but in the middle, it might use your credit card for other things. It might sign up for tons of like subscriptions, etc. Right? So those are like the manners that you don't want it to take, or the agents might peek through your, for example, your inbox, your Gmail inbox or something like that, right? You also, if you are a user, you feel like your privacy is invaded, but it may not necessarily be encoded in the end state. Although you can say that the whole trajectory is a state, you can encode all of the history in the state. I think that if that is the case, then probably yes. Yeah, yeah. So I think that is the one dimension. The other aspect is actually related to the first one. So it is true that you can evaluate, a lot of manner by observing the end state, but you still need to know what you are looking for. Right? If you don't really know, like for example, slamming the door is a thing that matters, you won't look for the traces of that. Yeah, only when it's very obvious, right? Only when the door is broken, then you realize that problem. But if it's not that obvious, then you may not really, know what to look for.
I think so.
Yeah. Okay. So yeah, so this is our method called the AutoLibra. It is very simple. The formulation of it is very simple. The input is agent trajectory, and the agent trajectory plus the human feedback. So human feedback is open-ended. So we allow any form of the human feedback. I will talk about how we collected this human feedback. And the human feedback are not rating. We don't give them a Likert score, and it's not preferences because we don't think it's very realistic in the real life that the customer get agents performing the same task twice and rate which one is better. A So it is not preference based. It's a purely open ended, and we have in this paper, we show that it can produce both this kind of a goal-oriented evaluation as on the left side, and it's also can produce like behavioral evaluation on the right side. On the left side, it's evaluating the goal, efficiency, quality, etc. On the right side, it's evaluating the behavior and the manner of the agents conducting these tasks. Great. But there's a problem of using open-ended feedback, because open-ended feedback is qualitative. It's inherently qualitative. I think there are two properties that make them qualitative. First is uncalibrated. For one, even if it's the same agent and the same task, one human might say, okay, the agent finishes its task. And then another human may have a different opinion. They may think that the agent is super slow, so they have to take over. So the agents might be exactly the same, completing the task at the same speed, but one human might expect it to finish faster, the other one is more patient. So it's uncalibrated, it's subjective. And the second problem is often too specific. For example, if you find the button is disabled, don't click again. So this is very specific to this task that is clicking this button, but so it cannot easily generalize. It's hard to be used as a metric. So it was impossible to directly use this kind of open-ended feedback for quantitative evaluation beyond the semantic analysis. So you can have like a positive and negative semantics, and you can calculate and then you can calculate the average of the sentiment. But beyond that, it is very hard to use open-ended feedback. So the idea of AutoLibra is that we can cluster a lot of feedback together. So it is not possible to use one single feedback as a quantitative measure, but it's possible that we can cluster multiple qualitative feedback, open-ended feedback together and produce a metric. For example, you can have like the button is disabled, and you can also have a positive one that the agent finds the option to save file before exiting, and it can also have another one that is a negative one about interacting with the drop-down menu. So all of these are about interacting with the UI. Some are positive, some are negative, and we can cluster them together, pack them into one metric that is evaluating the UI interaction. And the benefit of this is that first it's calibrated to a population. It's not just specific to one human. A lot of humans are giving their feedback, so it's calibrated to a whole lot of people's feedback. And the second is that it can generalize across different tasks. So it's not just specific to that button. It can also generalize to other menu interaction and any other UI interaction. So how does this process work? The first step of this is to break down the human feedback. So based on this task is for example, this task is to compare the prices and the chips for two iPhone model. The agent is doing good at the first, but then it chose the wrong model. And the feedback is that the agent didn't interact with the drop-down menu to choose the right iPhone model. And for this one, you can produce a new feedback in a structured form, which includes two fields. First field is the agent's behavior, and the second field is the human feedback aspect. So this is a very simple instance where the human feedback only has one negative feedback. In reality, some of the feedback have like multiple aspects. For example, this one, the agent did the right search but didn't sort by price. Then you have a positive feedback, use the right to query, and the negative feedback. So I want to emphasize here, it is not just a breaking down of the human's language, it's also a breaking down of the trajectories and match the trajectories behavior with the human feedback, because the aspect includes two different fields. And in practice, we found most of the large language model can perform this task fairly well, even if we just use relatively cheaper models like GPT-4o, they can already do very well at this step. So after we have these aspects from the human feedback, we can take all of these aspects from a lot of humans across all of the tasks together and cluster them. This is following our idea previously to make it generalized to different tasks. And in this case, we cluster them together. So the way that we cluster the feedback together is actually very simple. We just feed this feedback as input to some models, some language models, and ask it to generate the metrics in this form. In practice, this straightforward method have some problems. One problem, significant problem, is that if you have too many aspects, it might go beyond their context length. And even if it doesn't go beyond their context length, it might fail to reason if you have too many aspects and you want to cluster them. It is too hard a task for a model. So the way we perform it is to is to first do chunking. We chunk the aspect into smaller pieces and ask each of the chunk to generate the metrics, and we aggregated all of the metrics that we have collected from different chunks. And then we go through all of the aspect and match the aspect into the metrics. And you will find some of the metric aspect cannot be matched into the clusters. And then you can take all of the aspects that haven't been matched into the cluster and cluster this aspect again. And do this iteratively until all of the aspects find their cluster. So in this way, we can group these aspects together. And the reason why we didn't use embedding-based kind of a clustering method, which is more conventional and which is more conventional and widely used, is because we want the topic to match, and we also want the good behaviors and the bad behavior to be clustered together. So in practice, we found that even if we use a large language model based embeddings, they often separate the good behaviors and the bad behaviors, and it's very hard for us to match them. Although I think in this step, there are other alternatives that in the future people can investigate. For example, they can rewrite all of the positive to negative and then do embedding-based clustering. That will be left for the future research. In practice, we found that this kind of iterative clustering method works well as long as we use relatively stronger reasoning models like O1 or O3 or Gemini Pro. These models generally works very well in this step. So this is after this step, we actually produce a set of a metrics to evaluate the agents. Each of the metrics contains actually 4 different fields. First, we have a name for the metric. Second, we have the description of the metric. Third and fourth are the good behavior list and the bad behavior list. And each of the behavior is a summarization of multiple aspects that are highly similar. Some of these are actually very, very specific. And I will talk about when using these metrics, this is actually a good benefit. So in the third step, we can use this metric in evaluation. In the evaluation, we are mainly adopting LLMs judge because our metrics are saved in the natural language form, a structured natural language form. Although it is possible to generate the codes for evaluation, but in this paper, we stick to LLMs judge. Using this instance and all of the metrics that we have we can get the judgment from the large language models. So there are positive traits. So positive traits means the metrics that are rated as a positive. Negative traits means the metrics that are rated as negative. And they're not applicable ones. It means that the metrics are rated as an A. So basically, we do 3-way classification for each of the metric, and then we'll have these 3 kind of trees. Yeah, so we have in this step, we also found that LLMs judge performed reasonably well. Its a correlation with the human judgment is over 90%. You can check out the detail in the paper how we conducted the human evaluation. So this is the third step of it, and we also found that if you don't have like the examples I mentioned in the previous step, the LLMs judge correlation will drop a lot. And the last step of the AutoLibra is to check whether the LLMs judge results actually correlate with the human feedback. So this is important because in the previous step, although we can ask a human to evaluate whether the LLMs judge evaluation is good, but it's hard for human to directly annotate what are the aspects that are not evaluated by LLM. So it can humans can validate whether the LLMs judged on the existing metrics are good, but it's possible that there are metrics that have not been induced and also mentioned in the human feedback. So in the last step, we evaluated the alignment between the LLMs judge results, basically the traits that have been found by the LLMs judge, and the breakdown of the unseen human feedback. So we also break down this feedback that have not been used by LLMs judge, and we break it down into some aspect, and we check whether these traits are correlated with the aspect. So in this way, we can have like two meta metrics. One is coverage, the other is redundancy. Coverage means that what's the proportion of the unseen human feedback has been mentioned, have been evaluated by the LM. And we also have redundancy, which means how many metrics that are actually not used, not mentioned by the humans. So with these meta metrics, we can have like the feedback signal for improving the metrics. So in AutoLibra, the metric induction is actually a closed loop process. Based on these meta metrics, we can change the metrics that we induce and find the best metric set with the highest coverage and the highest and the lowest redundancy. So I will omit that part of how we did the optimization. You can check paper for that detail, but I want to emphasize what do humans care about? What are the results that we get from AutoLibra? So this is the first data set we evaluate. This is called CoGym from Dee's lab at Stanford. So on this data set, they have AI agent help human with various tasks like travel planning or finding related work, etc. And they ask prolific users to interact with the agents that they develop. And they collected over 300 pieces of real user feedback. I want to mention that these feedback are from prolific crowd workers. So the format are very arbitrary. I look at a lot of the feedback. It contains like a foreign language. It contains some password, etc. Basically, it is of relatively lower quality. But even if we have like, so I want to say this kind of feedback are very realistic. It probably will be the feedback if you develop this in the real world. Even on this relatively low quality set of user feedback, AutoLibra induce several metrics that actually make sense. If you compare it with the expert analysis of the trajectories, you'll find this, we can find a rough match between these two, like responsiveness and efficiency, communication clarity and notification are relatively equivalent to communication. And the error rate also matches with each other reasonably well. So basically, this can show us that the AutoLibra can induce its metrics that from the real user feedback, and it's more concrete than the feedback from the Asperg post-hoc analysis. So this gives us a relatively confidence that we can really mine and induce this evaluation metrics, understand what humans really care about through AutoLibra. And on the second data set, this is Zootopia. This is one of my work. We collected 100 pieces of annotation. And these annotations are actually from experts. So we annotated among the co-authors. We accumulate like 100 pieces of an annotation. And on the right, you can see the metrics that are induced by AutoLibra, like the goal achievement, outcome effectiveness, or conversation naturalness, efficiency. So these metrics actually match some of the dimensions that we designed before running the agents, including goal completion and believability. But outside of this, so I mentioned before in this talk that in the Zootopia, we designed 7 different dimensions. So only these 2 dimensions can be matched with the metrics that are induced by the AutoLibra. And there are a whole lot of dimensions like relationship, knowledge, secret, etc., that cannot really be matched with the AutoLibra induced metrics. And there are metrics that are mentioned by AutoLibra that are not mentioned, that are not part of the dimensions that we designed in the Zootopia, like negotiation tactic and strategic adaptability, etc. So it actually this actually surprised us that like the things that the human really care about in this kind of annotation actually mismatch with the dimensions. When we are designing this framework, design Zootopia, we build these dimensions based on like the theories grounded in sociology and the psychology, but they actually mismatch how humans will perceive the trajectories of the agents. And the last one, this is on Web Voyager, which is a web navigation benchmark. We use the annotation from another paper as a follow-up. Another paper that's a training like a web agent on Web Voyager. So we have like 100 plus annotations. And on the right, you can see the error recovery and adjustment, step efficiency, action redundancy. These are the metrics that are induced by AutoLibra. And navigation stuck, hallucination, prompt misalignment. These are the failure categories from the human expert from Web Voyager paper. And these are actually roughly matched together fairly well. And the error rate also matched very well. And there are some metrics that are induced by AutoLibra that actually are missed by human expert, even in the post-hoc analysis. So the human expert look at all of the agent trajectory and they try to categorize the failures. But these are things that the humans missed, like a query and search strategy efficiency or final output summarization quality. Those are the things that we can find with 100 plus annotations plus AutoLibra, but are not mentioned in the error analysis in the previous paper. And there are failure reasons from the human experts. They say this is a viral grounding issues, but but the problem is that the human experts merit this is like their understanding interpretation of the model behavior, but it's not that obvious that we can really induce that from the behavioral observation. Cool. So just to give you a short summary, in the previously, most agent work assumed that first the goal is known and encodes all of the requirements. And in AutoLibra, the human observe and give feedback after agent perform a task. So there's no assumption of the goal, a known goal or a close-ended goal. And second, previously, it is assumed that only end state matters. AutoLibra look at the whole trajectory and also induce these behavior evaluation metrics. And we don't make assumption about we know what people care about the agent. We don't. So we listen to the humans, we collect the human feedback, and induce the metrics that based on the human feedback. Cool. We can have a short pause here. Just have 4 more slides. So if anybody want to ask a question about the previous this time. Okay. Okay. So for the last part, I want to briefly mention that this is a work from intern worked with me during the summer on improving the agents based on the open-ended feedback. So yeah.
Who did have a question? I saw Michael put his hand up. I'm not sure if you saw the question.
Oh. Yeah, I was wondering if you've measured how AutoLibra performs on different models throughout time. So, like for example, like GPT-3 through GPT-4, and if like how it failed changed.
Yeah. So You mean using different model for AutoLibra, right? Or
Yeah.
different
Yeah,
agents?
see how it like if there's like a trend, like if the models are getting towards like better in this one area or worse in one area, is it, for example?
Yeah. So actually, I think we try to use a different language model for AutoLibra. I have mentioned it before. I don't have very concrete number to show here to compare different models in like the performance, because to evaluate AutoLibra, the only method is to do human evaluation because it's the evaluation of the evaluation is fairly hard. From our observation, we found that some of the steps will require a reasoning model to perform really well. For example, clustering these clustering these behaviors into metrics is a very difficult task for non-reasoning models. We found that if you use the GPT-4o for clustering this behavior, the clusters are very superficial. For example, they will cluster all of behavior on the same website together. So it will say, okay, this metric is for all of the behaviors that are on apple.com. Something like this, and it's fairly hard to generalize across different tasks. But if you use a reasoning model, it's easier. And for the elements judge step and the first breaking down the feedback step, actually using smaller model, using GPT-4 non-reasoning models are actually reasonable. And in the last part of my talk, we are using Gemini 2.5 Flash for all of the steps, all of the AutoLibra steps and the agents. And we show that this can improve the agent's performance. I think it's a fairly good evidence to show that the modern LLM are fairly suitable for AutoLibra.
Great, thanks.
That answer, yeah.
And I one question. So when you collect this aspect feedback pairs from the humans, do the humans see the entire trajectory when they annotate essentially? So what do you think about the element of hindsight essentially? Because the human, unlike the agent, can see the outcome of potentially incorrect actions, and there is in theory some information asymmetry, or is it not important, you think?
Oh, you mean because the agent human can see the whole trajectory, but the agent cannot see what will happen in the future.
Yes.
Yeah. So here we are not comparing human and the agents. We are asking the human to evaluate, to give a feedback to the agents. Actually, this is I think it's the bonus, because like the human, this is an advantage because the human can see the whole trajectory, so that it doesn't really need to guess what will happen in the future. For example, if they click on the wrong button, it goes to a completely undesirable state, and then the human will realize, it's very easy for human to realize that this is a problem. And LMS judge is similar to the human judge. She's similar to human. We will also see the whole trajectory. Yeah, I think this is because we are not using human for the agent task. We are only asking human to evaluate it. I think it's fairly reasonable to have this information asymmetry.
Thank you.
Cool. Yeah, great. I also see Raj comments. Yeah, I don't know if this is a question or not, but yeah, it's great. Yeah, okay. Let me wrap up really fast if you only have 10 minutes. So if we look at how humans and AI learn, there are a lot of mode of human learning. We learn from trial and error. And machine learning, we also have reinforcement learning that is very similar to the human way of trial and error, although I would argue that reinforcement learning is relatively less sample efficient in this case. And we also have like a human learning through imitation, behavior learning. In machine learning, we also have like behavior cloning or SFT that are inspired or similar to this process. But there's one aspect of the human learning that is not being seen as important, that is self-regulated learning. So for example, a 2-year-old kid may try to touch the outlet, may be very curious about it. And if the adult sees that, they will say no. They will ask the kid to stop. Although the kid may not know why this is wrong, but they will try not to do it again. And in fact, they will try to imitate this action. They would imitate the no. The next time they try to touch the outlet. And after they grow up, they will generally formulate this kind of self-regulated metrics or self-monitoring metrics that will be that are actually learned from the feedback from other humans, and that this will be affecting their future actions. So in this process, the AutoLibra can be well suited in the second step, that is to induce these kind of self-monitoring metrics from the feedback. The first step from the human, and the last step we can improve using various ways to improve the agent. We can do that through reinforcement learning based on the metrics that are induced by AutoLibra. And in this paper, we choose a very simple way, that is to do prompt engineering. We ask Gemini 2.5 Flash to update the prompt of the agents in order to improve the AutoLibra metrics. So here is the game and the environment that we studied. So this game is called Baba is AI. If you have played Baba is You, this is the AI version. So the agent need to control this triangle, this white triangle, this is the Baba. And to complete this task, you can see there are several rules there. The wall is stopped, so the gray blocks cannot be penetrated. And we also have like a Baba is You, which is the first rule, means that this is what the agent is controlling. And on the right, you have a door, you have a red ball, and there is win, but there's nothing as a subject. So to solve this task, the agent need to first change the identity, because there's the wall is stop cannot be broken. It cannot go through the wall. It should first change the identity of the door to the Baba to door. Basically push the door block to the location that the Baba is located, so that it form a new rule that is called door is you, so they can control the door after it changed the identity. And the second need to form the win rule, that is to push the ball into before it's win, to form the win rule, that is a ball is win. And then lastly, you need to touch the ball to win this game. So it's a fairly complicated game. It's a very simple observation space, a very simple action space, but fairly complicated. And a lot of these skills will require, for humans to require the metacognitive skills. But for agents, it's still a lot of skill to learn just through reinforcement learning, or at least for agents, the zero-shot performance is very, very low on this task. So we put AutoLibra in action to see if we can use AutoLibra in this kind of iterative learning procedure. We divided the whole game into 3 stages. Before each of the stage, the human provide the feedback, and the AutoLibra will induce metrics from this feedback. And then within the stage, we use the large language model prompt optimizer. Here is a Gemini 2.5 to improve the prompt of the agents. And then the agents will perform the task again and use the induced metric to evaluate the agent's performance until we see an improvement on the metrics AutoLibra induced. So this is iterative procedure. So after we see that improvement, we ask the human to provide the feedback again and induce new metrics and improve the agent based on all of the metrics we have thus far induced. And throughout the time, you can see, although we are only improving the metrics that AutoLibra induce, we are not improving based on the success rate. The success rate goes up through time. And we can also see that the agent learn a lot of things that are fairly amazing, like showing awareness of the map boundaries and then form self-referential rules. At the last, because it's a prompt engineering process, you can expect that the prompt gets more and more complex. At the end, the agents begin to overthink, and we can see the performance dip. That's the when we terminate the experiment. So we can do this in this iterative manner through different stages. So this is an example where we can use AutoLibra to improve the agent through learning from the human feedback. So in the past, it's a very we need the human to provide the preference pairs or provide ratings in order for agent to learn a reward model. But here the agents directly induce this metric from the human feedback to improve themselves. So this is a very interesting application of the AutoLibra. So lastly, I want to mention there, AutoLibra opens a lot of the questions. For first one, to which extent the human feedback is needed. If it's a personalization, of course, we want human feedback because there's no way that we can customize the agent for everybody before they interact with the human. But for the general task, what is the limit of language model providing feedback? In the whole paper, in the whole experiment, we only ask a human to provide feedback. But it's possible that we substitute the human with a large language model. It is possible that in this way, we can also induce useful metrics. But how would that compare to the human? And the second is that how can we collect more natural human feedback? So here we get the feedback from the end of the episode, but you can imagine that in the real world application, human users may not really provide the feedback if the task have been completed. So probably we should get this kind of feedback during the interaction. And I think the larger topic of this is how can we really involve humans, especially the normal users, not the experts, in the process of training and the evaluation so that we can really build the agents that humans care about. Great. I'm happy to take any questions.
Hao, thank you so much for coming, first of all. I would like to note that probably we have a couple of minutes because you and I have to get to Dee's meeting.
Yeah.
But so maybe we have time for one or two questions. I guess I'll start off. When you have multiple different dimensions of feedback, how do you decide how to weight the dimensions? And what happens when does feedback ever conflict?
Yeah. So we didn't weight different dimensions, but I think it's really good idea that we can learn like a weight for each of the metrics, especially when the agents improve itself in the future. It's possible some old metrics should be rotated out and there are new metrics rotated in. So probably we should let the weight to be more dynamic. Second, so when we are inducing new metrics iteratively, we provided all of the old metrics as a part of the context. So this will, I think, by and large, avoid the problem of like a conflict. But it's possible that some metrics are conflicting. We just didn't observe that.
Thank you so much. Any other questions?
No, but great presentation. Fascinating. Thank you.
All right. With that, let's close. Hao, thank you so much for coming. Really a pleasure. If anyone else has questions, feel free to leave either me a note in the Discord or put a question in the planning and reasoning Discord, and I'll make sure to ask Hao when I get a chance.